On August 3rd, 2026, a team of planetary scientists published a paper confirming something researchers have been watching build for the better part of a decade. Pluto's atmosphere, thin as it already is, appears to be genuinely thinning further. Its pressure dropping in a way that fits almost perfectly with a scenario some scientists have quietly worried about for years, that the atmosphere itself could eventually freeze solid and disappear from view entirely. This isn't speculation dressed up for a headline. It's a peer-reviewed result, published in the Planetary Science Journal, built from a decade of painstaking, indirect observation of a world so distant that no telescope on or near Earth has ever been able to see its atmosphere directly, using nothing more than the flicker of a background star's light to reconstruct what's actually happening on a planet nearly 4 billion miles away. That's the real weird thing happening on Pluto right now, and it's stranger and more scientifically real than almost anything a fictional headline could invent. To understand why a shrinking atmosphere on a small, frozen world nearly 4 billion miles away is worth paying attention to, you have to understand how anyone even knows Pluto has an atmosphere at all, since not a single spacecraft is anywhere near it right now and hasn't been since 2015, and likely won't be again for the foreseeable future, with no follow-up Pluto mission currently funded or scheduled by any space agency on Earth. Pluto is roughly 2/3 the size of Earth's own moon, sitting more than 30 times farther from the sun than Earth does. Cold enough that most of what we'd normally think of as gas exists there as ice, with surface temperatures typically hovering somewhere around negative 380 degrees Fahrenheit. Its atmosphere, when it has one, is made almost entirely of nitrogen, with smaller amounts of methane and carbon monoxide mixed in, all of it under a pressure so low that describing it in familiar units barely makes sense. Amanda Sikafous, lead author of the new study and a researcher at the Planetary Science Institute, described the total atmospheric pressure as only a few millionths of Earth's, present around a world she noted is 2/3 the size of our moon and roughly 30 times farther from the sun. That thinness is exactly why nobody can simply point a telescope at Pluto and watch its atmosphere the way you might watch clouds move across Jupiter. Even to the best space telescopes currently operating, Pluto appears as little more than a tiny, featureless blob of light, a handful of pixels at best, with no visible surface detail whatsoever, let alone anything resembling a directly imaged atmospheric layer. There's no spacecraft close enough to see it directly, and there hasn't been one since NASA's New Horizons probe made its historic flyby back in July 2015. The only time in history a spacecraft has ever gotten close enough to Pluto to measure its atmosphere directly, up close rather than by inference, a 9.5-year journey that itself remains the fastest and most distant planetary flyby any spacecraft has ever completed. So, scientists studying Pluto's atmosphere today rely on something considerably more indirect, but remarkably precise once you understand how it works, a technique called stellar occultation. Every so often, Pluto's orbit carries it directly in front of a distant background star, as seen from Earth. And for a brief window sometimes, lasting only a couple of minutes, that star's light has to pass through Pluto's atmosphere before it reaches us. As it does, the atmosphere bends and scatters that starlight, causing it to fade gradually rather than blink out instantly the way it would if Pluto had no atmosphere at all. Sikafous described the technique herself in a public statement accompanying the new study, saying she remains constantly amazed at how the simple act of watching starlight dim and then reappear allows scientists to study an atmosphere that thin, on a world that small, at a distance that extreme. By carefully measuring exactly how gradually that starlight fades, how long the star stays dimmed, and how gradually it brightens again as Pluto moves past, researchers can reconstruct the density, pressure, and even the haze content of an atmosphere they can never actually see, purely from the shape of that single dip and recovery in a distant star's brightness, essentially treating each occultation event as a brief, precise probe of the atmosphere's structure, sent in from millions of miles away for free by the geometry of the universe itself. For this particular study, Sikafous' team analyzed 10 separate stellar occultations by Pluto recorded between August 2017 and July 2023, 4 of which were observed simultaneously from multiple locations on Earth, giving researchers several independent readings of the same event to cross-check against each other and rule out local atmospheric or instrumental noise, skewing any single measurement. Some of that observational data came from dedicated professional observatories. Some came from smaller telescope networks and even individual observers positioned along the narrow path, where each occultation's shadow happened to fall, since the shadow of an occultation only sweeps across a limited strip of Earth's surface, sometimes just a few hundred kilometers wide, meaning researchers sometimes have to coordinate observation sites across entire continents just to make sure someone is positioned correctly when a given event happens, occasionally relying on amateur astronomers and small regional observatories to fill in coverage that professional facilities alone couldn't guarantee. What that decade of careful, patient occultation watching revealed is a genuinely strange pattern, one that becomes clearer and stranger the further back you trace it. According to background laid out in the new paper, and in earlier research it builds on, astronomers first confirmed Pluto had a detectable atmosphere at all in 1988, using the same occultation technique in an era when Pluto was still officially classified as the ninth planet, and personal computers were still a relatively new fixture in most research labs. From that point through 2015, the year of the New Horizons flyby, Pluto's atmospheric pressure didn't just stay steady. It increased, roughly tripling over that nearly 3-decade stretch, according to figures cited in the broader body of research this new study draws on, with the pressure reportedly doubling just between 1988 and 2002 alone, an unmistakably steep and sustained climb across every occultation measurement researchers managed to capture during that period. That increase, on its own, is already counterintuitive because Pluto had already passed its closest approach to the Sun, called perihelion, back in 1989, and had been slowly moving farther away into colder territory for the 26 years leading up to the 2015 flyby. An atmosphere getting thicker while its planet moves farther from its heat source sounds backward, but it's explained by something called thermal inertia. Pluto's surface ices absorb and release heat on a significant delay, meaning the coldest, most atmosphere-freezing conditions on the ground lag years or even decades behind the coldest point in Pluto's orbital position, the same way the hottest part of an Earth afternoon typically arrives hours after the Sun's most direct overhead angle at solar noon, just stretched here across a delay measured in decades rather than hours. After the 2015 flyby, occultation observations showed that rising trend leveling off. According to the new study's findings, Pluto's atmospheric pressure remained essentially flat, plateaued, from 2015 through roughly 2021, a stretch of apparent stability that lined up with earlier independent research, reaching similar conclusions, and one that, at the time, offered a reassuring middle ground between the decades of steady increase that preceded it and the decline some models had already begun predicting further down the line. Then, according to Sisyphus's team's analysis, something shifted. Comparing data from the 2015 through 2021 plateau period against a 2022 occultation, the team measured a drop in clear atmosphere pressure of about 7% at one specific altitude in Pluto's atmosphere, roughly 1,275 kilometers above the surface, and when the effects of atmospheric haze were factored into the models, a considerably steeper drop of roughly 16%, give or take about 2%, at a slightly lower altitude band closer to 1,215 kilometers. That 16% figure is the headline result driving the "atmosphere may be collapsing" framing now circulating in coverage of the study, and it's worth being precise about what it does and doesn't establish. It's a real measured decrease in atmospheric pressure over a roughly 2-year window, following years of stability, not a confirmed, ongoing collapse trend that's guaranteed to continue, and the paper itself explicitly stops short of declaring the atmosphere is now in permanent, irreversible decline. This isn't the first time a pressure drop like this has been reported either, which matters for how seriously to take the current result, and for understanding just how genuinely difficult this kind of measurement is to nail down cleanly. Back in 2020, physicist and astronomer Ko Aramatsu at Kyoto University in Japan, working with colleagues, reported results from a July 2019 occultation suggesting Pluto's atmospheric pressure had already dropped by roughly 20 to 21% compared to a 2016 measurement, a finding that generated its own round of Pluto's atmosphere is collapsing coverage back at the time, years before the current study's own version of that same headline. That earlier claimed drop didn't hold up as a clean, permanent trend in every subsequent measurement. Other researchers found evidence of a plateau continuing into 2020, effectively contradicting the idea of a steady, uninterrupted decline already underway. And the new Sisyphus study itself describes a plateau persisting through roughly 2021 before the more recent decline appears in the data, meaning the 2019 measurement that caused such a stir at the time now looks, in hindsight, more like a single noisy data point than the start of an unbroken downward trend. That back and forth isn't a sign that scientists don't know what they're doing. It's exactly what you'd expect when you're trying to measure extremely subtle changes in an almost impossibly thin atmosphere using indirect starlight measurements gathered a handful of times a year from a world moving through one of the most extreme, slowly evolving seasonal cycles of any object in the solar system, where a handful of noisy readings can easily be mistaken for a trend until enough additional data accumulates to tell the difference. And Pluto's seasonal cycle really is extreme, on a timescale that makes any short-term measurement genuinely difficult to interpret with full confidence. Pluto takes 248 Earth years to complete a single orbit of the Sun, and its orbit is both unusually elongated and tilted at a steep angle relative to its own rotational axis, meaning different parts of the planet experience dramatically different amounts of sunlight across that 248-year cycle, similar in concept to Earth's seasons, but stretched across a timescale longer than the entire history of powered human flight, longer even than the time since Pluto itself was first discovered by Clyde Tombaugh in 1930. Pluto reached perihelion, its closest approach to the Sun, in 1989. It won't reach the opposite extreme, aphelion, its farthest point, until the year 2114, according to the orbital mechanics laid out in coverage of the new study, a full 125 years after that closest approach, meaning the summer Pluto experienced around 1989 is still, even now, only slowly giving way to a winter that won't fully arrive for nearly another century. That means Pluto is currently roughly partway through the outbound leg of a single Plutonian season that started before most people alive today were born, and won't complete until decades after most of us are gone, a genuinely rare scientific position to be in, watching, in real time, an atmospheric process that unfolds on a scale spanning multiple human generations, using data collected mostly by people who will never personally see how the story ends, and relying on a scientific record that only stretches back to 1988 in the first place, meaning researchers have direct atmospheric data covering barely 15% of a single Plutonian year. The physical mechanism potentially driving the pressure drop comes down to a tight, direct coupling between Pluto's atmosphere and its surface, a relationship considerably more direct than anything comparable on Earth, where our atmosphere is largely decoupled from surface ice behavior in any comparably immediate way. According to the new study, Pluto's atmosphere exists in what's called vapor pressure equilibrium, with the nitrogen ice covering large parts of its surface, meaning the atmosphere's thickness is essentially a direct readout of how much nitrogen ice on the ground is warm enough to sublimate, turning directly from solid ice into gas versus how much is cold enough to stay frozen solid, with essentially no liquid phase involved at any point in the process, given how far Pluto's surface conditions sit below nitrogen's melting point. As Pluto drifts farther from the Sun following its 1989 perihelion, less sunlight reaches the surface ice, and given enough time, more of that ice should settle into its frozen state rather than releasing gas into the thin atmosphere above it, which would show up, observationally, as exactly the kind of pressure decrease the new occultation data appears to be picking up. Sisyphus herself was careful, in public comments on the study, to describe the underlying physics as still not fully understood, noting specifically that the relationship between Pluto's atmosphere and its surface ice properties remains an active, unresolved area of research rather than a fully solved problem, one complicated further by the fact that Pluto's surface isn't uniformly covered in ice of the same type, thickness, or thermal behavior, meaning different regions of the planet could plausibly be releasing or absorbing atmospheric nitrogen at different rates simultaneously. There's a related visually striking consequence tied directly to this pressure drop, one that connects the raw occultation numbers to something closer to what people might picture when they imagine something weird happening on another world. Pluto's atmosphere isn't just nitrogen gas, it also contains haze, layers of fine particles formed when sunlight breaks down methane and other carbon-based molecules high in the atmosphere, building up into complex hydrocarbon compounds that eventually settle downward, and which are responsible for Pluto's distinctive reddish-brown surface coloring, a finding that came directly out of the 2015 New Horizons flyby data, when the spacecraft's own cameras captured Pluto's hazy layers backlit against the Sun in one of the mission's most striking farewell images, revealing dozens of distinct haze layers stacked in the thin atmosphere that scientists hadn't fully anticipated finding. According to the new study, as atmospheric pressure drops, that haze should behave in a specific, predictable way, thinning out and settling toward lower altitudes, retreating closer to the ground, the same way fog on Earth can thin and sink under certain conditions. The occultation light curves Sisyphus's team analyzed showed exactly this kind of signature, changes in how gradually starlight faded and reappeared in the lower atmosphere, consistent, according to the paper, with haze particles settling downward on a timescale of a year or less, layered on top of the broader pressure decline in the data. And in at least one of the light curves the team examined, they noted small, sharp spikes that appear consistent with intermittent buoyancy waves rippling through the lower atmosphere, a subtler weather-like phenomenon layered on top of the broader, slower seasonal trend. It's genuinely important to be clear about how uncertain the bigger picture still is, because that uncertainty is part of what makes this an honest, ongoing scientific story, rather than a settled, dramatic conclusion. Different volatile transport models, the specialized computer simulations researchers use to predict how Pluto's ice and atmosphere should evolve together over its 248-year orbit, don't currently agree on where this trend leads. Some earlier models, referenced directly in the new paper, have predicted Pluto's atmosphere could genuinely collapse, essentially freezing out almost entirely, as the planet's seasons progress further past perihelion, a scenario researchers have been actively modeling and debating since at least the mid-1990s, long before any occultation data existed that could actually test which version of that prediction was correct. Other more recent modeling work reaches a different conclusion, suggesting the atmosphere is likely to persist throughout Pluto's full orbital cycle regardless, largely because of a specific geological feature New Horizons discovered in 2015. A massive glacier of nitrogen ice sitting in a giant impact basin nicknamed Sputnik Planitia, roughly the size of Texas, which appears to hold enough nitrogen in reserve, combined with high thermal inertia in the ground beneath it, to keep feeding the atmosphere gas even as conditions cool elsewhere on the planet, effectively acting as a kind of enormous, slow-release reservoir that could buffer the atmosphere against exactly the kind of collapse other models predict. Sikafus's own comments on the new result reflect that same open uncertainty directly, saying plainly that her team's work suggests the atmosphere has recently started decreasing in pressure, while adding that she's hopeful further data collected over the coming years to decades will be enough to specifically confirm or refute that trend. Language that's about as far from manufactured urgency as a genuine scientific finding gets. And a reminder that even the researchers closest to this data are treating it as the opening of a longer investigation rather than its conclusion. Pluto isn't behaving strangely in isolation either, which adds an extra layer of real intrigue to the timing of this particular finding. In May 2026, just months before Sikafus's team published their atmospheric pressure results, an entirely separate group of researchers, led by Ko Aramatsu, the same Kyoto University astronomer behind the earlier 2020 Pluto pressure drop finding, announced evidence of an atmosphere around a completely different, far more obscure world in the outer solar system. A roughly 300 to 500 kilometer wide object with the unwieldy technical designation 66125333 2002 6FOND 93, located nearly 40 times farther from the Sun than Earth, roughly 6 billion kilometers out, in the same general Kuiper Belt region Pluto calls home. Using the exact same stellar occultation technique observed during a January 2024 event when the object passed in front of a distant background star, Aramatsu's team found that starlight passing behind this small world didn't disappear instantly. Evidence of a thin atmosphere estimated at somewhere between 5 and 10 million times thinner than Earth's own, an almost unimaginably faint wisp of gas clinging to an object most people have never heard of, published in the journal Nature Astronomy. If independently confirmed, this would make the tiny world only the second object beyond Neptune, after Pluto itself, ever found to host a genuine gravity-bound atmosphere, a discovery Alan Stern, the lead scientist behind NASA's original New Horizons mission and someone who wasn't involved in this newer study, publicly called an amazing development that sorely needs independent verification, adding that the implications would be profound if the finding holds up under further scrutiny. That second discovery matters for understanding Pluto's own atmospheric story, because it reframes what's happening on Pluto as potentially just the most visible, best studied example of something that might turn out to be considerably more common across the icy distant reaches of the Kuiper Belt than anyone previously assumed possible. For decades, the working scientific consensus was straightforward. Pluto was the exception, the one small, cold, distant world with enough surface ice and internal geology to sustain any kind of detectable atmosphere at all, an oddity rather than a representative case. A second independently confirmed Kuiper Belt atmosphere, even one 5 to 10 million times thinner than Earth's, complicates that picture directly, and researchers involved with both findings have specifically called for further observation, including with the James Webb Space Telescope, to figure out whether Pluto and this newly flagged object are truly rare exceptions, or the first two confirmed members of a much larger, previously invisible population. There's also a strange, entirely separate real-world thread tangled into this story right now. One that has nothing to do with atmospheric physics, but everything to do with why something weird happening on Pluto has been circulating in the news at all this year. In comments reported alongside coverage of the new atmospheric findings, NASA Administrator Jared Isaacman publicly floated the idea of reinstating Pluto's status as a full planet, a classification it lost in a controversial 2006 decision by the International Astronomical Union, made in significant part because of the growing recognition that Pluto was just one of many similar icy bodies out in the Kuiper Belt, rather than a unique planetary outlier. Isaacman's comments arrived while he was simultaneously endorsing a proposal to cut NASA's science budget roughly in half, a combination planetary scientist Adine Denton publicly criticized on social media at the time, noting the strangeness of pushing to make Pluto a planet again, while, in her words, decimating the careers of the very researchers who actually study it. That tension is genuinely part of the current, real news environment surrounding Pluto, even though it has no bearing whatsoever on the actual physics of the planet's thinning atmosphere. If anything, several of the researchers covering the new occultation study pointed out that a second, independently confirmed atmosphere on another Kuiper Belt object arguably undermines rather than strengthens the case for treating Pluto as a unique planetary exception, since it reinforces exactly the scientific reasoning that led to Pluto's 2006 reclassification in the first place. So this is the real, current, and genuinely unresolved story behind something weird happening on Pluto. And it's stranger, considerably better documented, than anything requiring an invented mystery. A world nearly 4 billion miles from Earth, visited by a spacecraft exactly once in 2015, and unlikely to be visited again for a very long time given no follow-up mission currently exists on any space agency's schedule, is having its paper-thin atmosphere tracked entirely through the way it bends starlight. A technique so sensitive it can detect pressure changes measured in millionths of Earth's own atmospheric pressure across a world 2/3 the size of our moon. A decade of that painstaking observation now shows a real measured pressure drop following years of stability, arriving at almost exactly the point in Pluto's 248-year orbital season where some, though not all, physical models predicted a decline should eventually begin. Nobody involved in this research is claiming certainty about where that trend leads next, whether toward Pluto's atmosphere gradually thinning into near nothingness over the coming decades, or toward a stable, sustained equilibrium propped up by the enormous nitrogen reservoir sitting in Sputnik Planitia. What they are claiming, on the record, in a peer-reviewed paper published just days before this recording, is that the atmosphere has genuinely started to change, measurably, for the first time since anyone began watching it closely, and that the only way to know what happens next is to keep watching starlight flicker and fade behind a tiny distant world, patiently for years or decades still to come, exactly the way scientists have already been doing, one careful occultation at a time, for nearly 40 years.